Hello everyone. So in this video, I want to show you how to implement a PID controller in Matlab in order to evaluate its performance, how to fine-tune the control parameters in order to improve its performance, and finally we'll have a look at two other design methodologies for PID controllers beyond the one we talked about in the previous video, which is the Ziegler-Nichols tuning rules. Now, coming back to what we've done last time in the previous video, we had looked at how to apply the Ziegler-Nichols rule number 2 to this specific plant transfer function. Then, applying the second rule, we came up with the critical gain and the critical period of the system, which were respectively given by 30 and 2 pi over square root of 5. If you're not too sure about what I'm talking about, I highly recommend you go and watch the previous video where we had solved together this specific example. Now, based on those two parameters that were found by applying a proportional control gain to the plant and varying its value until we've obtained sustained oscillations at its output, we had then mapped those two to the three control parameters known as Kp, Ti, and Td for the PID control law. Now, our job as control engineers doesn't stop here, because the next step is to make sure that what we found in terms of control parameters, either KCR and PCR, and implemented that directly into this alternate form of a PID controller, and we've also talked about this alternate form in a previous video, or using those three control parameters implemented directly into the standard form that says Kp times 1 plus 1 over TIS plus TDS. Either one will work fine, but yet we have to ensure that the values we found for those control parameters give us the expected performance. But before we looked at how to implement this controller in MATLAB and evaluate its performance, let's ask ourselves, what are we expecting? Well, what we expect out of Ziegler-Nichols tuning rules, either rule number 1 or rule number 2, is not the best optimized performance we can think of. Because again, Ziegler-Nichols tuning rules only give us an educated guess on those control parameters. In no way, shape, or form we have to take those for granted, implement those inside our controller, and call it a day. Because as we'll see in simulations in a moment, for example, in this specific case we looked at, well, the maximum overshoot will be on the order of 60%. That could be fine for you, but in most applications, 60% of overshoot is not acceptable, meaning that those only serve as first guesses. So we'll have to come back and manually tune them, or tune them using some alternate design methodologies to refine the performance. Okay, so when we talk about MATLAB implementation of such control law, the first thing we need to do is to define or rewrite those transfer functions in polynomial forms. Because as you know, this is how MATLAB works in terms of defining transfer functions. So let's first rewrite our plant transfer function in a polynomial form. So I'm just going to multiply everything out here. That's going to give me s cubed plus 6s squared plus 5s. Okay? And for the purpose of our implementation, we're going to use the alternate form of our PID control law in MATLAB. Instead of the standard form, we're going to play with that one. So let's rewrite that in a polynomial form so that we can easily implement it in MATLAB. So this is going to be this 0.6 over 8 times KCR times PCR doesn't change. Then to make our life easier, let's define a new parameter as A, and A being simply the ratio of 4 over PCR, all this over S. All right? So I'm going to say where A was defined to be equal to R4 over PCR, meaning that in a polynomial form, this PID control law would simply be equal to S squared plus 2AS plus A squared, all this over S, like that. Okay? So this is how we're going to implement our plant transfer function in Matlab. And this is how we are going to implement our PID controller in Matlab as well. So the first fine-tuning methodology we'll have a look at is a very simple one, in the sense that what we'll aim at doing is simply change the position of our double zeros, which is provided by our controller, right? Because you remember that the PID control law provides us with two zeros at the same location in complex plane, and that position being S equal minus A, or in other words, S equal minus 4 over PCR. So we'll manually change the position of the zeros by changing this controlled parameter, the critical period, PCR, regardless of the value we found according to Ziegler-Nichols rule number 2, because this 2 pi over square root of 5, right off the bat, if we just implement that in MATLAB, you'll see that the performance won't be the best. It will be far from being optimal. So by changing this parameter, regardless of this value, maybe we'll divide this by 2 or multiply it by 2, we'll see that we'll be able to then change the position of our double poles via this relationship, and therefore change our control law. So that's going to be a crude first approach in order to fine-tune the performance. Now the second methodology we'll have a look at to design our PID control law is to automate the iterative process of trials and errors to select our control parameters. But instead of playing with one control parameter, two control parameters, and perhaps even three control parameters, if you consider that A and PCR could be changed independently from one another, and that's going to be the approach of our second methodology here, we'll just lump all those terms here into a single constant that we're going to call K. So we're going to come back to this original transfer function and simply rewrite it in this form, where our K was set to be equal to 0.6 over 8 to KCR PCR. But in the second approach, we'll just change K as being one parameter independently of what it physically represents, and independently of our second tuning parameter, which is going to be A. So that's going to give us only two parameters to play with instead of three, and that will ease up the design process quite a bit. Now this design methodology of iteratively, is that even a word? Performing iterations, let's put it this way. So we'll define some bounds on the value of K we'd like to evaluate and the values of A that we'll also evaluate. And we're going to run a double for loop in iterations. Okay? We will iterate on the values of K and A. So it seems very simple, yet the name of this design methodology is very fancy and is known as PID Computational Optimization Design. Okay, that's our second way to tune our PID controller. And then we're going to come back after playing in simulations with MATLAB based on these two design methodologies. The first one, just changing the double pole location by changing only PCR manually and then applying this computational optimization design idea. And then we're going to come back to the whiteboard and have a look at another design methodology, but let's save that for later on, okay? So now let's go to the computer and let's apply those design ideas. All right, so here we are in Matlab, and the first thing we'll do is to evaluate the performance of the PID controller we designed using Ziegler's Nickel rule number 2. So as usual, I start any Matlab program with my CLC, close all, and clear all commands. And next, what I want to do is to define our planned transfer function. So if you go back to the example we've been playing with, we had GP equal 1 over S times S plus 1 times S plus 5. All right? So let's define that in terms of a polynomial that MATLAB can understand. So our numerator is simply 1, and our denominator will be a polynomial, which will be S cubed plus 6S squared plus 5S plus 0. And we're going to turn that into a transfer function using the TF command, as usual, like that. Okay. And now that we've defined this transfer function, let's go and verify that the value we found for the critical gain and the critical period match what we see in simulations. Okay, because the work was done analytically on the whiteboard. But just as a sanity check, let's confirm that those two values for the critical gain and the critical period are indeed the right ones. I want to say verify previously determined values of critical gain and critical period. And if you go back to the example, we had found analytically that the critical gain was 30 and that our critical period was found to be 2 pi over our critical angular rate or angular frequency, which was square root of 5. Okay, so that was our critical gain, and that was our critical period for the sustained oscillations. Based on that, let's apply this critical gain to our plant to obtain the open loop transfer function as being simply the gain times our plant transfer function. And with this open loop transfer function, we can also calculate the closed loop transfer function, which is simply G open loop over 1 plus G open loop. So open loop transfer function with KCR. That multiplies the plant transfer function, and that will be our closed loop transfer function. Okay, so next we can just draw a figure that would plot the step response of our closed loop transfer function, and let's plot that in, say, black. I'm going to put the grid on, and we'll define the axis as being, for the time, we'll go 0 to 30 seconds. And step response will go 0 to 2, so that we can see any overshoots. All right. So let's run this program and see what we obtain in terms of, oh, not overshoot, sorry, but sustained oscillation. There's no PID controller in the loop, it's just static gain K, for which the value was the one that created those sustained oscillations. And as you can see with K equal 30, the amplitude of the oscillations remain constant. So that's good news. So let's see what would happen if that critical gain gets just a little bit below the critical value of 30. And that makes sense. The gain doesn't push the poles directly on the imaginary axis. We're getting close to the imaginary axis, yet we're still in the stable or asymptotically stable region of the complex plane, and thereby we see a dampening of the oscillations like that. Now again, 30 puts the poles directly on the imaginary axis, and this is why this specific gain of 30 was found to be the critical gain. All right? And let's see what would happen if we go a bit higher than that. We would expect the poles to be now on the right-hand side of the complex plane. Okay, so like a very erratic behavior. If you go to 35, well, maybe I would need to change it. Let's just go 31. Okay, so you see that it's getting unstable. We see that the magnitude of these oscillations would tend to grow with time. So this is an unstable region. So 30 again is our critical gain value. So that confirms the analytical calculation we did on the board. And for the critical period, let's zoom in. Yeah. And 2 consecutive peaks. And let's obtain, click, 1.57 seconds, and here 4.38. So if you go back to the code, if you check the value for a critical period, 2.8 is pretty much what we found by looking at the graph. Okay, 1.57 to 4.38 is, yeah, about 2.8-ish. So that makes sense. So it's just a good sanity check here to make sure that our analytical calculations did provide us with the right values for KCR and PCR. This is a good thing to do because the design of Ziegler-Nichols in terms of control parameters for the PID controller depends entirely on those 2 critical values here. All right, so now that we've cleared this up, let's calculate the transfer function of our PID control law. I'm going to say PID Ziegler-Nichols rule number 2, design. And if you remember, our analytical transfer function for a controller was equal to 0.6 over 8 times our critical gain value times the critical period times our double zero located at s equal minus 8. Right? A pair of zeros on the same location in the complex plane over S. So one pole at the origin of the complex plane, and the location of the double zero is quantified through A, which was set to be equal to 4 over the critical period PCR. All right, with that in mind, the first thing we need to do here is to define this constant A that quantifies the position of the double zeros in the complex plane. It's 4 over PCR again. And then we have everything we need to come up with the numerator of our controller transfer function. So 0.6 over 8 times KCR times PCR times our polynomial. If you remember, we did the work on the board and we found out that it was S squared plus 2AS plus A squared. So S squared, 2AS, and A squared for the numerator. And the denominator of our controller transfer function is simply S, so S plus 0. Okay, we'll turn that into a transfer function. Non-GC, then GC, like that. And then because we want to evaluate the step response, we have to come up with the open loop transfer function of our PID controller in series with our plant transfer function like that. And based on that, we'll come up with the control or the closed loop transfer function. It's G open loop over 1 plus G open loop. Same old, same old. We'll create a new figure for this. And then we're going to say step response of our closed loop transfer function. And let's draw that in black. We're going to say all done because we will compare the step response for the PID Ziegler-Nichols rule number 2 design with other design methodologies in a few minutes. So hold on. And then grid on as well. Let's see what we obtain. All right, so this is a step response by applying the PID tuning methodology, which is Ziegler-Nichols rule number 2, and by using those control parameters as is within the control law. So no fine tuning whatsoever, we just applied them directly, and this is the response we got. So this is expected. We've discussed this on the whiteboard previously, where the performance you get right off the bat isn't the best. And indeed, you see that you have an overshoot of about 60% and a settling time of about between 10 and 15 seconds. For most practical applications, such large overshoot is not adequate. So that tells us that we need to go back to the first educated guess that we get by applying this heuristic rule for tuning a PID controller and play with it by hand. I'm going to say PID Ziegler-Nichols manual fine-tuning because the performance is not the best as expected. So as discussed, the way to do it is to change manually the critical period by hand. So let's make it twice what it was before. Okay? And this is how we can now affect the position of the double zeros in a complex plane, because that relationship that ties the critical period PCR to A still exists. All right? So as you saw, I just did twice the original critical period, regardless of the value we had evaluated analytically. And then that will affect A, or the position of the double zeros. So let's come up then with the new PID controller based on the new A and the new PCR values. So it's going to be the same analytical formula to come up with the numerator. So that would be S squared plus 2AS plus A squared for the numerator, and denominator remains the same, S plus 0. And then redefining the new transfer function of the controller, coming up with the opening transfer function by applying this controller to our previously defined plant transfer function, GP, and then closing the loop, and then doing the step response of this new closed loop transfer function, and to compare with the previous one in black. So black will be the original design according to the textbook material, whereas this one was fine-tuned by hand. How did we do it again? Just by multiplying the previously obtained critical period by a factor 2, and based on that, recalculating the position of the double zeros analytically, coming up with a new control law like this. Let's run that. Wow, much better. You see the red line here. Let's add some legend to it so we can better see what's going on. I'm going to say the black curve corresponding to the original design, whereas this one going to be the fine-tuned version. Let's run that again. Okay, so again, you see the black response, the original response that we had gotten or obtained. That was the one with 60% overshoot, compared to the fine-tuned version of it, which is the red curve, and you get about 20-ish% overshoot. Pretty good improvement. Turned out this fine-tuning was somewhat easy to do. I just changed this value, but I mean, you could play forever and, you know, fine-tune it or changing those values manually. And you see the response now is about 35% overshoot. We went to 2. Let's see what would happen if you go to 2.2. See if you could decrease a little bit more the overshoot. Yeah, less than 20% now. Pretty good, pretty good. So feel free to play with this parameter until you get satisfactory performance. Okay? So that was the first approach to fine-tune the Ziegler-Nichols octane design. The second way is what we call the PID, computational optimization design. So this is just an automated double for loop that will go through some predefined values for our K constant, where K was obtained by lumping all these parameters into a single K static gain. We've discussed that on a whiteboard again. And by also varying our A value. So now instead of having to, you know, possibly vary more than 2 values, we're left with only one gain and one A value that we're going to change independently from one another, although they're they were related to one another through Ziegler-Nichols rule number 2, but within the computational optimization design idea, we consider that those two parameters are not related. Okay? That would give us the opportunity to play with both independently. All right, so I'm going to define the range for the K value of this gain to be from 2 all the way to 50. And this for loop, and within this for loop, I'm going to define another for loop that will vary my A value from 0.05 all the way to 2 with an increment of 0.05. I'm going to end this for loop before I forget to do so. Okay, so for each individual K and A pair, I'm going to have to define my numerator of my transfer function for the PID control law. And again, this version, again, lumps those 3 parameters, so this constant times KCR times PCR as just K, and that's the K we're varying between 2 and 50 in this example, times the polynomial that defines the position of the double zeros, and then again, that's the same as usual, so S squared plus 2A plus A squared. And the denominator doesn't change because all the PID adds in terms of poles is one pole at the origin of the complex plane, so 1 over S essentially. Next, I combine the numerator and the denominator into my transfer function for the current value of K and A. All right. And then, as usual, I'm defining my open loop transfer function by being controller times plant transfer function, and then coming up with a closed loop transfer function, G open loop over 1 plus G open loop. Now I'm going to step or apply a step unit input to this closed loop transfer function over a time period of, say, t. So I'm going to find my time range between 0 and 10 seconds. 0, say 0.1, all the way to 10 seconds. But then I want to save the output of my step response into a variable that we'll call y, y being the output of the plant, because we'll need to analyze automatically this output, and specifically want to get the maximum value so that we can calculate automatically within this double for loop the maximum overshoot. So we're going to save the max value of this output as ymax, is a variable here, by using the Matlab max command. All right, based on that, I can easily calculate the maximum overshoot as being ymax minus the steady state value, which will probably be equal to 1, right? Minus 1, and we'll turn that into a percentage, so times 100. So now this is where, as a designer, you have the opportunity to, oh no, where's my smaller symbol? Oh, here it is. To specify what you want in terms of maximum overshoot, to call your design a good one. In this case, we'll seek control parameters for K and A that would provide us with a maximum overshoot between 1% and 10%, such that we do better than the manual fine-tuning that we did, which gave us 20% overshoot, compared to the original Ziegler-Nichols rule number 2 that provided us with 60% overshoot. So let's see if we can find some combination of K and A that would give us a maximum overshoot between, say, 1%. Oh no, where did that go? Here. Between 1% and 10%. So whenever we're going to get a solution for the current pair of K and A values that we're analyzing within this for loop, we're going to save this combination into an optimal solution. So the current one, meaning that we'll have to specify the index, and we'll increment the index whenever a suitable solution is found. And specifically would like to save the current K value that provided us with a max overshoot between 1 and 10%. Also would like to save the current A value that quantifies the position of the double zeros and complex plane, and with the associated max overshoot value. Now I'm going to end this if, and then I'm going to, for ease of analyzing our analysis, I'm going to save all these solutions into a sorted variable. I'm going to call sort or sorted optimal solution. I'm going to use the Matlab sort rows function that will sort all of our optimal solutions based on the maximum overshoot value with increasing value. All right. Okay, so let's run this and see if we can find some values. Oh, yeah. I've forgotten to initialize my K variable here. Sorry about that. I want to CT. Let me just clear the command prompt. CLC. Oh, it's still running through. Okay. So let's see what we found. Good. So these, oh, a lot of them. The first column of this variable that we call sort optimal solution corresponds to the gain value k. Next to it is its associated value for a, and both of these combined together gave us the third column, which is the overshoot values. And again, you see that the only solutions we kept in the end were those that provided us with an overshoot of less than 10%. All right, so these are all admissible solutions that would meet our quote-unquote specification in terms of overshoot here. Okay, fantastic. So let's see what would happen if we end up choosing the combination that provides us with the lowest amount of overshoot. So that would be 30 and 0.05 for K and A respectively. Let's say sort optimal solution, the first one in the array. 1, 1 would be this gain value K, 30. And then for the A value, I'm going to just say this is this first row, second column for A, like that, such that we like to evaluate this particular solution. All right, so now that we've sorted out the K and A values, we can do the same as usual. So we'll define essentially the numerator of our PID controller with those two specific values. Denominator was previously defined, but just for completeness, I'm going to redefine it here. And then defining the PID transfer function, GC, the opening transfer function, closed loop transfer function, as per usual. All right, and then I'm going to do the step response, as we did previously here. So step, closed loop transfer function. We're going to draw this one in blue. So now we'll have three responses on the same graph. The Ziegler-Nichols rule number 2, as is, the fine-tuned version of it, and then what we call the computational optimization design. Is a third way to obtaining a PID control parameters. Nice. So let's see. It's going to take a little while to go again through the double for loop. So we have to be patient. Well, look at that. Look at that. So original design, Ziegler-Nichols rule number 2, fine-tuned version of it, and what we've obtained using the computational optimization approach. We pretty much got rid of any overshoot, and that was expected because we selected the K and the A values based on the fact that that was an admissible solution that was providing us with a maximum overshoot of about 1.something%. And that's what we see here. The price to pay of decreasing the overshoot is a longer stabilization time, as you can see, right? And the more overshoot you get, the smaller the stabilization time you'll get. So you kind of get both simultaneously with that kind of design idea. So let's see what would happen if we use the other end of the spectrum in terms of the admissible solutions that provides us maximum overshoot between 1 and 10%. And let's pick the last set of values in this variable we call sort opt solver for solution, such that instead of having 1% overshoot, will be closer to about 10% overshoot. So we're just selecting the last entries. And if I remember, that was for a maximum overshoot of 9.99%, something like that. Yeah, pretty good, pretty good. Yeah, about 10%, 1.1 in terms of max overshoot. And compared to the previous solution that we had about 1%, we decreased the stabilization time quite a bit. Yet is going to be the solution that provides us with the longest stabilization time among all three design methodologies. But that is expected if you want to minimize overshoot. Again, the price to pay is longer stabilization time. Yeah, so that pretty much summarizes the MATLAB evaluation of the Ziegler-Nichols rule number 2 design methodology that we've done analytically on the board. And also showed you how to verify with MATLAB the obtained values for the critical gain and the critical period. And also how to manually fine-tune it to improve the performance, in this particular example in terms of max overshoot. And finally, how to implement a computational optimization design methodology to run through a double for loop and to run through a range of K and A values and automatically saving the ones that provide you with the performance you're after. In that case, maximum overshoot between 1 and 10%. Good. So let's go back to the board. And what we'll do on the board is to talk about yet another design or tuning methodology for PID controllers, known as the ITAE optimal design idea. All right, so welcome back to the whiteboard. We're going to have a look at yet another design technique for PID controllers. This time, we're going to have a look at the ITAE optimal design methodology. So with this design approach, the objective is to find out optimal control parameters in the sense that we want to find parameters that will minimize a cost function or an objective index. That cost function being the integral of time absolute error criteria defined mathematically as the integral between 0 and infinity of time times the absolute of the tracking error signal that exists between the reference signal and the actual output of the transfer function times dt. So the way it's going to work in terms of applying this design methodology is that we'll first have to come up with the characteristic equation of the closed loop transfer function, then organizing the coefficients of the polynomial, which is our characteristic equation, in this fashion here, okay? So we'll have to set the AJ coefficients such that they correspond to those coefficients according to this polynomial. And then we're going to come to this big table that does the mapping between those coefficients and some parameters which are all function of the natural frequency of the system. Okay? And as you'll see in the next example, those coefficients, the AJ coefficients, will all be function of the unknowns that we're looking to solve for, specifically the K gain of our PID controller, as well as the position of the two zeros of the controller. All right? So let's have a look at the example that we've been using thus far in terms of designing our PID controller, where we had our plant with one pole at the origin, one pole at S-1, and another pole at S-5. Okay? And let's see how we can optimize the control parameters in order to minimize the ITAE criteria. So, if you go back to what we had, again, that was our transfer function of the plant, 1 over S times S plus 1 times S plus 5. Now, for this design methodology to work, we have to write our PID control transfer function as being equal to our gain k and multiplies the position of both zeros, denoted as Z1 and Z2, respectively, which are unknown, over our pole at the origin. Okay, so as I said, the first step is to obtain the characteristic equation of the closed loop transfer function. And because we know that our PID controller will be implemented in series with our planned transfer function, we know right away that the characteristic equation will simply be equal to 1 plus GC times GP equals 0. So characteristic equation of our closed loop transfer function will then be equal to 1 plus GP times GC equal to 0. Not too bad. So 1 plus our planned transfer function, same old, times our controller, which is k times s plus our first 0 times s plus second 0 over our integrator equal to 0, because this is the characteristic equation. Okay, so let's put everything onto the same denominator. Let's cancel out the denominator because we have this equal to 0, and let's see what we end up with. So essentially we're going to get s times s plus 1 times s plus 5 times s, that's for this term, plus k s plus z1 s plus z2 equals 0. And obviously we get this over this whole denominator, but because again this is equal to 0, it gets cancelled out. So all in all here, we're going to get s to the power 4 plus s to the power 3. Is that it? Let me take it one step at a time. So s times s cubed plus 6 s squared plus 5s plus here, what do we have? We have k that multiplies s squared plus z1 plus z2 times s plus z1, z2, all this equal to 0. And here we're going to get s4 plus 6 s cubed plus 5 s squared plus, and then I'm going to continue with k s squared plus k z1 plus z2 s, and then plus k z1 z2 equal to 0. Okay, so now I'm just going to group together the coefficients that I have here in front of the s squared term, like this, and the rest is already organized properly. So we're going to get s4 plus 6 s cubed plus 5 plus k times s squared plus k times z1 plus z2, all this being the coefficient that multiplies s, then plus k times z1 times z2, and multiplies s to the power 0, obviously, all this equal to 0. All right, so now this is my A4 coefficient, my A3, my A2, A1, and my A0 coefficient. Because now I have reorganized my characteristic equation in the right polynomial form that I needed in order to extract those AJ coefficients, remember? And now all I have to do, well, obviously this is order 4, n equal to 4, is to go back to the big table I had drawn previously, select the row for n equal 4, and do the mapping between those coefficients and what we had in the table. Specifically, we had A3. Okay, so A3. Okay, so A4 is 1, but there's not much to do with it, right? Because according to the table, it's just equal to 1. So 1 equal to 1 doesn't help me. My A3, according to the table, was 2.1 times omega n. 2.1 omega n. But now my A3, according to what we have here, is 6. All right? A2, according to the table, was 3.4 omega n squared. But now what we have for A2 is 5 plus k. A1 is this, according to what we have, but as per the table, it was 2.7 omega n cubed equal to k times z1 plus z2. And lastly, my A0 in the table was omega n to the power 4 equal to A0 here, which is k times z1, z2. And because we had in order 4 for our closed-loop transfer function, or the order of the characteristic equation of that closed-loop transfer function, it means that we have 4 equations to play with. And the unknowns we're trying to solve for are simply k and the position of z1 as well as the position of z2, the two zeros provided by the PID controller. This is what we're trying to solve for. And solving those equations would guarantee us that those control parameters that are still unknown will be optimal in the sense of minimizing the ITAE criterion. All right? So first things first, everything is function of omega n on the left-hand side of those 4 equations. So the first thing I want to do is solve for omega n, which is simply going to be 6 over 2.1. I don't have the numerical value for that, but that's fine. We know how to do it. And then once we have omega n in terms of number, we can then solve for the first control parameter that we need in order to implement our PID controller, which is the gain k, which is going to be simply 3.4 times omega n squared, omega n being coming from that first equation, minus 5. And now I solve for the first one. And now we have 2 equations with 2 unknowns, z1 and z2. The beauty of those equations is that we don't need to solve for z1 separately than z2. Why is that? Well, because if you go back to the form of our controller transfer function, which was k times z plus z1, times s plus z1 times s plus Z2 over S, right? This is a PID controller with two distinct poles in the complex plane, as opposed to having what we had previously. If you remember, we had considered that both zeros were on top of each other, so all we had was S plus, we had quantified that as A and square over S, because both zeros were considered to be on the same location, yet here we have two distinct zeros in the complex plane. Okay? It gives us more freedom in terms of design, essentially. But if you multiply those two parentheses together, and anyway, you'll have to do it in order to implement this in Matlab, because again, Matlab takes transfer functions in terms of polynomials. So it's going to be k times s squared plus z1 plus z2, both multiplying s like that, plus z1 times z2. So as you see, in order to implement this PID control transfer function, you don't need to know what is the value of z1 and the value of z2 independently, because if you can find for z1 plus z2 as one unknown and z1 times z2 as another unknown, then you're good to go, correct? And those equations allow us to do just that, all right? So we found k using the first two equations, and the last two are there to help us or to allow us to solve for z1 plus z2 and z1 times z2. So just solve for these unknowns and substitute them back directly into this form of our PID control law. All right. Now, what do we expect in terms of performance when we select our control parameters to minimize the ITAE criterion? Well, you have to go back to this criteria in terms of mathematical quantification of it. Because what it does is that it penalizes errors that would stick for a long time in the control loop, okay? So because it penalizes long-lasting trajectory tracking errors, it means that we can expect a relatively short settling time, yet probably at the expense of a larger overshoot, because the ITAE, again, aims at minimizing response that would take a long time to converge. So that's what it would do. A large overshoot is the price to pay for rapid settling time. So that's what we expect. Yet, let's confirm that together by looking at the Matlab implementation of it together. Okay, so welcome back to Matlab. What we have left to do here is to implement the PID ITAE optimal design that we've discussed on the whiteboard together. This one's going to be a quick implementation. There's nothing too difficult about it. So if you remember, the trick is to solve for the natural frequency, omega n, and according to the four equations we've obtained, because we were dealing with a fourth order system, the first one was used to solve for omega n, and that was based on the big table that you saw on the whiteboard. Next, we're going to use the second equation to solve for the gain value k. It's going to be our 3.4 times our omega n square and minus 5, okay? And then the last two equations that we have are there to provide us with the solution for z1 plus z2. So, because again, there's no need to individually solve for z1 and z2 as they appear in the transfer function of our PID controller. All we need is z1 plus z2 as a variable, and then also z1 times z2. And according to the equation we had, that was equal to 2.7 times omega n cubed divided by my k value, which was 6 over 2.1. and then for Z1 times Z2, this one is obtained according to omega n to the power 4 divided by k. Good. So now we have everything we need in order to implement a PID controller designed with a specific design methodology, which again is aimed at minimizing the ITAE criterion. So based on that, we can define the numerator of our PID controller as being this gain value times. Now, this time around, our numerator is going to be different than the one we've been using so far in this particular example, because so far we had assumed that we had a pair of zeros on the same location in a complex plane, and that's why the zero locations was quantified by a single variable being our A value, okay? But now we consider that we have two distinct zeros, such that the numerator would look like S squared plus Z1 plus Z2 times S plus Z1 times Z2. Okay? Then the denominator, that doesn't change. And be again S plus 0. And then no surprise here, defining the control transfer function as, num and den combined into a single transfer function with the Matlab TF command, like that. And then G open loop, G close loop, same old, same old. And then doing the step response. Let's do this one in green. We haven't used green so far, such that the legend will now be the first three design methodologies combined with the fourth one being the ITAE optimal design. Okay, I think we have everything we need to evaluate all four PID design methodologies together. Again, it takes a while because of the double for loop. There we go. What do we see here? The original solution in black from Ziegler's nickel provided us with a large overshoot on the order of 60-ish% and a large stabilization time. So we said that wasn't good enough. Then we redesigned the Ziegler nickel design methodology manually to provide us with about 20-ish% of overshoot, yet with a somewhat long stabilization time. Then we said, okay, let's apply the computational optimization design idea, and that gave us the blue curve here with a very good overshoot in terms of percentage. We're talking about 10% overshoot. Yet look at the stabilization time, okay, among the worst between all design methodologies considered. But if we apply the ITAE design methodology, we see that we still get the same overshoot as the original Ziegler Nichols rule number 2, so about 60%, yet the stabilization time is very good, okay, and is actually the best among all four design methodologies. So we have to ask ourselves, is it what we expected? The answer is yes, because you have to remember that the ITAE objective or criterion that this design idea seeks to minimize means that we want to penalize long-lasting trajectory tracking error, right? So in other words, we want to stabilize the system very rapidly. Yet, again, the price to pay to get the best stabilization time is a large overshoot, okay? But that's the idea with the ITAE. So if that's what you want to have in terms of performance for a given application, go ahead and implement this design methodology. If, on the other hand, what you want to do is to minimize the maximum overshoot, yet pay the price of a longer stabilization time, then perhaps you could implement a computational optimization design methodology. So there's no good and bad here. It's just about what you want in terms of performance out of your PID controller. Okay? These are just 4 design ideas that you can use to tune your PID controller, but there are many other ones in the literature and some textbooks as well. But that at least gives you a backbone of design methodologies that have gone through the test of time and have been implemented in many industrial settings and applications successfully. So use them, play with those design ideas. Hope you have fun. Hope you learn new ideas about how to tune PID controllers with this video. And until next time, keep up good work and see you soon.